So we're going to be basically paying attention to the octet, right? And when I talk about the octet rule, uh, we're talking about stability. So at the end of the day, everything wants to be like the noble gases for the most part. Transition metals are going to be our little exception. And you guys remember electron configuration, where this here represents our s orbital?
Yeah, the subshells.
Yep, that's right. Our s
Yes.
subshell, that's right. And this is our p subshell. Okay. Now, when we're talking about the octet rule, we're really just looking at the S and P because that's going to represent that outer shell. So if we think about the atom, we have the nucleus in the middle, and then we have, and I'm just going to draw it very generically, we have the energy levels. Now we know it doesn't look like this because each of the different orbitals have their own shape. I mean, each of the subshells have their own shape. So these are going to represent these periods, these outer shells. And so, as we remember, each of the different orbital or subshells have their own shape. This guy was like a circle. This guy was like dumbbell. This guy was like four-leaf clover. So they all each have independent shapes that are going to be associated. Now, when we look at it, we're going to be looking at that outer shell. When I'm talking about that outer shell, it's going to be the electrons that are going to be in that outer part. Those electrons are going to be available for bond, the ones that are in the outer shell. So that's what we're going to be looking at to determine whether or not they're available for bonding. Now, we know that the noble gases are stable. And the reason why they're stable is because their outer shell is completely full. And so they've gotten everything that they need. They have stability associated with it. Now, all of the other elements, they want to be like the noble gases. They want to have that stability associated with it. Now, the elements that are transitions, they're going to be a little bit different. They're going to find other ways to find stability. And that's the same thing with the latinoids and the actinoids. So these guys are also going to behave differently. They're going to find different ways of being stable. But the other elements, they are going to try to reach their octet, okay? Meaning that they're going to have their outer shell completely full, like the noble gases. Now, as with anything in life, we always want to try to find the easiest way and the lowest energy way of accomplishing things. Nobody wants to sit there and nobody ever sets out to say, I'm going to go the hardest path to get to where I want to go. Everybody says, I'm going to try to find the easiest way to get to where I want, right? Isn't that true? Wouldn't you guys all agree to that?
Yes.
Okay, good. I would hope so, right? So these guys, the elements are going to be no different than us. They're going to try to find the lowest energy method of trying to get their octet full. So in the case of like lithium could either try to gain 1, 2, 3, 4, 5, 6, 7 electrons to be like neon, or it could just lose 1 electron to be like helium. What do you think it's going to want to do?
Lose one.
It's going to want to lose 1. And when you lose an electron, what is the charge on the electron again?
Positive.
Are you sure? Electrons.
Electrons are negative, so
Electrons are negative, and protons are
positive.
positive, right? So pro, positive,
Yeah.
So we know protons are positive, electrons are negative. Now, if we have lithium, which is our atom, and we lose 1 electron, what is going to be the charge on the overall atom?
Positive, right?
Positive. That's right. Yep, that's right. So we know that this is going to be positive. So we know that things that are in group 1, because they're always going to only want to lose 1 electron, they're going to be positive. They're going to have a positive value associated with it. Okay, so lithium, when it forms an ion, it's going to be lithium plus. Okay, And that's how we write the ion. Okay. Now, if we come over here and we have like fluorine, what does fluorine want to do? How is it going to try to be like a noble gas? Do you think it wants to gain an electron, or do you think it wants to lose an electron?
Jane?
It's going to want to gain, right? Because if it gains just one electron, it's going to be like neon. So it's going to gain that one electron. So then it's going to have a minus charge associated with it. Okay. Now, when we talk about forming these compounds, these are called ionic compounds. It's going to be based upon charge. So if I have lithium and fluorine coming together, lithium is going to give up its electron, fluorine is going to take its electron. Okay, so it's going to be kind of give and take. Now, what happens when you have a positive and a negative?
They attract?
They're going to attract. So then they're going to come together and form LIF. Okay, and they're going to have to balance each other charges completely. You'll notice there are no charges up here at all because they're completely balanced. We have a plus and we have a minus. They balance each other totally. Now we call this compound lithium fluoride. Okay. Now we know that this is fluorine. To let us know that that's the end of the compound, we put IDE at the and replace that IN with. So then that lets us know that's the end of the compound. It also lets us know that the fluoride is the negative ion. Do you guys get that? So you'll notice instead of saying fluorine, we call it fluoride. Okay, so it's called fluoride because it's the ion, and it's also the end of the compound. So when we talk about nomenclature and when we talk about writing the chemical formula, the positive always goes first, and the negative always goes towards the back. Right? And it's kind of like in life. Do you guys have you ever had to give somebody bad news?
Yes.
Yes. Okay. So let's say, for instance, Juanita was talking to me and she was going to let me know I was going to be fired. So she'd probably come in with something good first, right? You want to give somebody good news before you have to give them bad news, right? Oh, chemistry was a great class. Your students love you, but you're fired. So doesn't that make sense? Because, you want to not make it so bad. You want to give them that good news first and then the bad news. So when we think about it, we always want to remember we want to put the positive stuff first, our positive ion first. So that lithium ion is going to be first, and then the negative is going to be last. Does that make sense?
Yes.
Yeah. I heard somebody laughing in the background. Okay, so
Wait, is that just for ionic compounds or just like any compounds in general, like naming them?
that's with ionic compounds. You're always going to put the positive first for your ionic compounds, and
Okay.
then your negative. Yeah. When you're talking about covalent compounds, we know that they're sharing. So there's no positive, there's no true positive and true negative, you know. Okay. So let's say we have magnesium and we have chlorine. Okay. So if we have magnesium and chlorine, what is going to be the charge on magnesium when it forms an ion?
Positive.
Positive what? Here's magnesium. Is it going to be one positive? Is it
Three.
going to be positive three?
Three.
Are you
Yeah,
sure?
positive.
So,
Yes.
Or two?
what was that?
I was
No,
thinking
no, no,
maybe
no, no.
two.
It's two. It's two.
It's
I
two.
I, mi- I
Yeah.
miscounted.
Yeah. So, because we were starting here, so we want to go back. So that's one, two. So we'd have to lose two electrons to be like neon. So then that means it's going to be 2 plus. Okay. And now chlorine, which is here. What about that guy?
It'd be negative.
Negative. Okay. Okay. So since we have 2 plus and then 1 negative, how many chlorines will we need to balance out, or how many chlorides would we need to balance out our magnesium ion?
2.
We'll need 2 of them. Okay, so when they all come together, it should be MgCl2. Okay, now what's going to be that name? Think about what we did up here. What did we call this guy? This guy was called lithium fluoride. So what do you guys think this is going to be called?
Would it be magnesium chloride or magnesium? Yeah.
That's right. And so because we always rely on them balancing out each other's charges, we never have to tell us how many you have of each. Okay? Does that make sense? Because we're relying on them balancing out each other's charges. Magnesium chloride. Okay? Now,
We we only use the Greek prefixes for the covalent compounds.
that's right. That's right. We only use the
Okay.
prefixes for
Just
the
making sure.
covalent compound. Yep. Okay. So I'm going to go ahead and see how many of you guys are here. Do we have a lot of people here today? Actually, this is probably the most people we've had in a long time. Okay, so what we're going to do is I'm going to go ahead and put up a couple of elements that are going to be bonded together. And I want you to figure out the charges of each of the ions first, and then how many you're going to need to make that compound. Okay, and I am going to show you. So I'm going to show you guys how to do something real quick. Let me get a whiteboard first, and then I'll show you. Give me 1 second. Let me see if I can get my brain to work here for a minute. Whiteboard. Okay, so here are going to be your elements. We're going to have so you guys are going to write them down because I'm going to put you guys in a group together. Then we're going to come back and report to each other because I think you guys learn better that way rather than me answering all the questions and stuff like that. So we're going to have calcium and nitrogen. We're going to have, now aluminum is always going to be a +3. Okay, I'm letting you know that now. Aluminum is always going to be a +3. It's a post-transition metal, but it's always going to be a +3. Okay. And let's see, we're going to have selenium and francium. Oops. Oops. And we're going to do oxygen and well, let's do sodium. Okay. Let's see. So let me put you guys in groups. So well, first off, you can write these down. And then when you guys get into the room, one of you guys, if you hit share screen and put a whiteboard up, you'll be able to sit there and make a whiteboard. And then you guys can use your your periodic table, and you guys can discuss it with each other. But the idea is that I want you guys to come back here and then talk about what you guys came up with. Okay. Now, I know that some of you guys have your kids with you and everything like that. Still interact. It's okay. We've heard kids all before, and those who don't have kids, don't be tolerant. And so that way everybody can kind of interact, and then don't be scared to chime in. Tell us what you think. Okay. Is that cool? Can you handle it?
Yes.
Okay. So we're gonna test this out. So let's see. We want to break you guys up. So what you guys can do is, if you guys go to the top of the page, it'll say you're sharing, or Dr. Henry is sharing your screen. It'll say like a green thing at the very top. There'll be three dots. And if you select those three dots, you'll see something that says annotate. Do you guys see that?
I'm sorry, what three dots did you say?
So at the very top, you'll see, like, if you hit select Dr. Henry's screen, you click on that, then you'll see a little thing that pops up, and then there'll be three dots. You'll see three dots, and it'll say more in some cases. Do you guys see the three dots?
I see a little pen.
Oh, you see a pen. Perfect. So then if you see that pen, go ahead and select that pen, right? And so that's usually for annotate.
Oh, okay.
Okay, perfect. So if you go to it, you'll see a little menu on the side. And then that menu, there'll be a little thing that says, it'll be an arrow. It'll look like this. It'll look like an arrow and a line. Okay. If you run over it, it'll say save. So if you click that, it'll save what you've done. Okay. So if I click mine, you can save it as a PNG, or you can save it as a PDF. And then if you hit open, it'll open it up for you. So then that way you guys have something to share on the screen, or you guys can just write it on the whiteboard when you guys get there. Okay. So let me put you guys in groups, and then rooms. Okay, how was it? Are you guys there?
We're here. We
Okay.
can figure out how to write on the whiteboard, but we were
Yeah.
just like trying to do it on our own.
The pen disappeared when
Yeah,
we
the
were in
pen
the groups.
disappeared.
Oh, really?
Yeah.
So
Oh,
we're writing it down.
okay. Well, we'll see what you guys got, right? Okay, so let's talk about the very first one. So, what is going to be the charge on each of the elements? Calcium is going to have what charge?
It'll be two positive?
That's right. And nitrogen?
Three negative?
And so then how many of each will I need?
I think Mark or Noah said that we needed to make it like six.
A total of 6. That's right.
Total of six to balance it out.
And you guys are going to let me just put that. There we go. 3 negative. There we go. Okay, so I need a total of 6 in my charges. So then I need how many calcium will make up 6? I'll need 3, right? So that's going to give me a total of 6 positives
And two
And then-
nitrogens.
and 2 nitrogens. That's right. So then my chemical formula is going to be Ca.
3 and 2.
Okay. Okay. So now what is the name of this compound?
Calcium nitrate?
That's right. Calcium nitride. Oops. Okay. What about selenium and francium? So what is going to be the charge on selenium?
Would it be 2 negative?
That's right. It's going to be 2 negative. And francium?
I was looking for that one. I'm still trying to find it.
Anybody want to help her out?
Is it 1 negative?
One like, yeah, it's 87.
Oh,
So
87. Okay, I found it.
So would it be 1 negative or would it be 1 positive?
1 positive.
Frame has a plus charge.
You said, what was that? Okay. So then how many of each will I need to balance each other out?
one selenium and 2 francium.
Okay. So then it would be what comes first? What would be my chemical formula?
Would it be francium because it's positive?
Okay. And there'll be 2 of them. Okay, so then what will be the name? You guys there? Did I lose you?
Like francium, selenium, something. I'd
Francium. If I can get it to type.
Is it francium selenide? Is that what he said?
That's right.
Okay.
Okay. And last one. It's going to be the charge on the oxygen.
Would it be 2 negative?
That's right. And then the sodium.
1 positive?
That's right. So then how many sodiums am I going to need to balance out how many oxygens?
Need 2 sodiums.
Okay. So my chemical formula should be
Na2O.
and then the name.
Would it be sodium oxide?
That's right. Okay, so you guys seem to get this, piece of cake, not too bad, right?
Dr. Henry, so the elements in the first group are like 1 plus, and then in the second group, 2 plus, and then you skip the transitions, and then you go to like the 13, huh? And then it'll be like 3 plus, and then 4. And that one could be
Yep.
plus or minus, and then 3 negative, 2 negative, 1 negative, and 0.
That's right.
Okay.
Yeah. And so if you take a look at the screen that I have up right now, that kind of shows you that, right? So group 1 is always going to be plus. Group 2 is going to be 2 plus. The next one, these guys are going to be 3 plus, right? They just happen to always be 3.
Okay.
And then aluminum is always going to be 3 plus. Okay. Now the other ones, the other post-transitional metals, those are going to be different. Okay. So we'll talk about that here in a minute. Okay. So as I told you, these are going to be forming ionic bonds. Some of the characteristics of ionic bonds is that they're going to be held together by the fact that they're attracted to each other. Those opposite forces, that plus and that minus. Now, almost all of the ionic compounds at room temperature and at normal pressure, they're always going to be solids. So they're always going to form what we call crystalline structures. And so they're going to have a defined geometric shape. Now, we've also talked about those charges, how they're going to be charged up. And at the end of the day, that compound always has to add up to 0. Now, these structures, these compounds, these bonds, these are strong bonds, that plus and minuses, they're strong bonds. And so these guys at room temperature, like I said, they're always going to be solids. Now, when we melt these guys, if we put enough heat, and it takes a lot of heat to melt them, a whole lot of heat to melt them. But when we melt them, or if we put them in water, they can also be good conductors of electricity. So here's an example of sodium metal. So sodium metal is added with chlorine gas. And so at the end of that, you're going to get the formation of salt, sodium chloride. Now, what happens, as I told you earlier, is that the sodium is going to give up one of its electrons to chlorine. So then your sodium is going to have a plus charge, and your chlorine is going to have a minus charge. And then they're going to form this lattice because of those charges, that plus, minus, plus, minus, plus, minus. And so you're just going to get the alternating of that plus, minus in this structure that's going to keep it together. And so this is an example of a salt crystal. And this is just showing you that sodium lattice. Now, this is just showing you that when you melt it, let's say we melt that sodium chloride, we put up enough energy and enough heat, we can actually melt it. I know on our stove we can't melt salt, but enough heat will actually get it to melt. And in that situation, we're able to get electric current flowing through it. And so it's good at conducting electric current when it's melted. When it's a solid, it doesn't conduct electricity, okay? Because it's completely balanced. What's happening is that you're loosening up the interaction between the positive and the negative, and that allows it to kind of reorganize itself with the electrons and pass on the electron. Okay, so we've talked about, those are examples of monoatomic ions, okay? Now, when we talk about those monoatomic ions, the positive ions are called cations because they're positive, meow, cat ions. And then the negative ions are called anions. We've already talked about how to name them, right? And so you're always going to put the positive first, and then in the case of monoatomic ions, the negative always has the "ide" associated with it. So here's an example. If I have bromine minus and barium 2 plus, so what is going to be my chemical formula and what is going to be my name? And don't all you guys yell at me at once. You're so talkative. Noah, are you there?
Sorry.
Do you want to help me out? So for the very first one, we have bromine minus and Ba2 plus. So what would be the chemical formula? And then how would I
Barium bromide.
barium bromide? So that would be the name. So what would be the chemical formula?
BaBr2.
BaBr2. Okay, good job. Look at that teamwork. Okay, what about if we have potassium and fluoride? What's going to be the charge on my potassium?
Positive.
So what is the symbol for potassium?
K.
And then what's going to be the charge on the fluoride?
Negative.
And what's the symbol for fluoride?
F.
Okay, so how many of each am I going to need to balance each other out?
One.
So we got KF. And you said it's going to be called?
Potassium fluoride.
Okay. Okay, so then that brings us to our transition metals. So our transition metals, transition, that term means what? Sophia, what do you think transition means?
Becoming.
Becoming, or how about changing? Right?
Yeah.
Okay. So because transition metals don't have a defined charge, they can change their charges depending on who they associate with, how you use them. So they can form different types of ions. So let me give you an example. Iron. You could have iron 2 plus. You could have iron 3 plus. Those are your two most common, but you can also end up having iron 4 plus. Okay. So all three of these exist in nature when they're forming. So it just depends on who they're interacting with and then how you use it. Okay. So because of that, we have to tell the charge on those transition metals. And the way that we do that is by using what we call the Roman numerals. So are you guys familiar with your Roman numerals?
Yes.
So everybody knows that 1 is going to be I. 2 is going to be I. 3 is going to be I. 4 is going to be IV. 5 is going to be V. 6 is going to be VI. 7 is going to be VII. 8 is going to be VII. 9 is going to be IX. And 10 is going to be X. Okay.
Who knew Star Wars could be educational for chemistry?
Pardon me?
Who knew Star Wars could be educational for chemistry?
Yeah, that's true, huh? So you guys are all familiar with it. You're feeling comfortable with that. So what does the Roman numeral represent again?
The positive charge.
It's going to be the charge. That's right. And
Or
it's
just,
always,
yeah,
you're right.
any
It's always
charge?
it's gonna be the charge on our transition metal.
Oh,
That's right. Okay, so let's say I had copper 3 plus. So how would I name that ion? Because this one here was called iron 2 plus. So then, or iron 2 ion. So what do you think we're going to name this guy?
Copper ion.
That's right. Copper 3 eyes ion. Okay.
so ionic compounds, you always put ion at the end.
So
Or you
if
could
you
just
have
use
just,
iron too.
yeah, so if you have just the ion itself, then that's what you'll put ion at the end. Not the compound. You never put anything at the compound. But if it's just that ion, if we're just talking about copper 3 plus, then you would always put ion at the end.
Let's see.
And so if I was talking about the fluoride ion, I'd call it fluoride ion. If it's just the F by itself, F minus.
I have a question.
Yep.
Does the Roman numerals just work with the positive charges?
Yes. And it's just the transition metals and the lantanoids, and then sometimes metalloids and actinoids.
Okay, thank you.
Okay. Good question. Okay, so now remember when we talked about diatomic elements? Do you guys remember your diatomic elements?
Have no fear of ice cold beer.
Yep, that's right. Have no fear of ice cold beer. That is correct. Well, there's one diatomic ion, and that's mercury. Mercury 1 is always written as a diatomic. So anytime that you have mercury 1, you have to write it as this Hg2 2 plus. So when we're talking about mercury 1. So that's the way we're always going to end up working with it. So let me give you an example. If I have mercury 1, oxide, how would I write that chemical formula? So anytime we see that mercury 1, the first thing that we want to do, we want to try to write it out in that form. So we're going to write Hg 2.
2O.
That's right. Okay. So we know that this is a plus, and we know what is the charge on the oxygen? Anyone there?
Is it 2 negative?
It's 2 negative. Okay. So we have 2 plus, 2 negative. So then I just need one of these and then one of these. So then my chemical formula should be, as Noah was saying, Hg2O. Okay. So what if I have this? I have mercury 1 phosphide. So mercury 1, what is that going to look like? Let's write that ion.
It's the Hg2 and 2 plus.
Okay, so then let's write the phosphide ion. What does that look like?
E2.
Are you sure P2? Where's
Oh,
phosphide located?
3, -3.
3 negative, that's right. P3 negative. So this has a 2 plus, this has a 3 plus. So then how many of these am I going to need? And then how many of these am I going to need? How many mercury 1s am I going to need? How many phosphides am I going to need?
2 phosphide and 3 mercury.
That is correct.
Why does mercury have 2 plus?
So mercury 1 has 2 plus because it's when it's at normal state, normal conditions, it doesn't like to be by itself. It's not very stable, so it immediately pairs up. And so that's the only way that it finds some type of stability to be maintained. Otherwise, it's even more volatile than what it is. So in this case, that'll be 2, 4, 6. So it'll be 6 mercury, Hg6, P2. Okay. Questions? Any questions? Okay. 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 Whew. So what would be the names of Mn2 plus, Mn3 plus? And then what are the formulas of nickel 2 ion and nickel 3 ion? So what is Mn? What is that?
The manganese?
Manganese. So it's manganese. And since there's a 2 plus, what should be the Roman numeral that we use?
The 2 ice.
That's right. And then ion.
And then ion, yeah.
That's right. Okay. And then the next one.
manganese 3I ion.
What would be the chemical formula for nickel 2 plus? I mean, damn it. Nickel 2.
Nickel 2 plus.
That's right.
You gave it away.
I know. My mouth sometimes.
And nickel
Okay.
3 would be Ni 3 plus, 3 plus.
Okay. Okay. Good job. Okay. So we have polyatomic ions. Now, what does that mean? Now, when we talk about polyatomic ions, we're talking about compounds that are covalently bonded together. So in this case, the nitrogen and the hydrogens are covalently bonded together. They're acting as a single unit that has a single plus charge. This guy is called the ammonium ion, and its chemical formula is NH4 plus. Okay. And it's acting as a single unit that has a single plus charge altogether. So it's acting together with a single plus. The hydroxide ion is OH minus. So it only has a single minus charge. Okay. These guys are covalently bonded together. They're interacting covalently. So when I say covalently, that basically means that they're sharing the electrons. But they have this extra, in this case, an electron has been removed. And in this case, an electron has been added. So if we're talking about these two guys interacting together and we're trying to write its chemical formula, since it's 1 plus and 1 minus, we would just write NaH4 OH. And if you notice how it's written, you notice that all of the H's are not written together, right? You have NH4 OH. That typically lets us know that this is ionically bonded, okay? Because we're separating those H's to make sure that we know that they're two separate things that are interacting, okay? So then we'd call this compound ammonium hydroxide. Okay, questions?
So when you put them together, you don't have to write their charges.
Nope, that's right. Because their charges are always going to cancel each other out. They always have to be balanced, right? Always add up to 0.
A little bit concerned. I checked my emails and you graded our group presentations like weeks before they were even due.
There's no way I graded your group presentations. I haven't touched any grading. What do you mean?
Sorry, just that for some reason it says it's 0 out of 100 on the group presentations already. It's weird.
Let me fix that because I know what happened.
It's
The
okay.
date was wrong. So let me fix it and then so I have not graded it. It automatically does things that it's not supposed to do yet.
Oh, it's fine. It's fine.
Yeah. But no, I'll fix it because I'll be getting 50 emails tomorrow, about it. So
Thank you.
yeah. And I apologize that if the date pops up wrong initially, then it automatically puts zeros, and then sometimes it does what it wants to do. It has a mind of its own. Technology possess. Okay, so I'm going to share with you. We have that sheet. I call it my chemical packet. Okay, so let me see if I can flip this so you guys can see it. Can you guys see it?
Squinting.
Yes.
Yes.
20. Let me see if I can make it a little bit bigger. Now you guys also have your own packet of this. And if you guys go to Mesa, there should be some left. I think I have a few left at different spots. So Mesa at all of the campus except Fireball. Fireball is in the library. So here, these are the common polyatomic ions. So these are the ones that we mostly run into. Okay. Now, since again they're common, you're going to see these quite a bit. I put these on the table. I'm not pushing you guys to memorize them, but the more you use them, the better off you be. Right. And there are certain ones that come up more frequently than others, but it kind of gives you an idea of how things work. Right. So for instance, let's take a look at chlorate. Chlorate is ClO3. Okay, do you guys see that? And it has a single minus charge. Chlorite, that ITE, is ClO2. Okay, now I can also have one called hypochlorite, which is just going to be ClO minus. Now, what is the difference between chlorate and chlorite? Look at the chemical formula. Tell me the difference between the two.
There's less oxygen in
That's right.
hypochlorite.
So there's going to be less oxygen. So hypochlorite has one less than chlorite. So hypo means under. So basically it says under chlorite. So that basically means that we have one oxygen less than the chlorite. Chlorite is one oxygen less than the chlorate. And then if we have one oxygen more than that chlorate, we call it perchlorate. Okay, so per is short for hyper, right? Do you guys know what hyper means?
Yes.
Yes. So when you're hyper, you're like off the walls, right? You're too much, right? So perchlorate means that you have one oxygen more than chlorate. Okay. Now, this is going to be the trend for everything, right? So when we go through nomenclature, we're going to use that 8 is our starting point. Ite is 1 less than. Hypoite is 2 less than our 8. And if we say per, that means we have 1 more than our per. I mean, than our 8. Okay? So let's play with this one here. So if I have carbonate, and carbonate is CO3 2 minus, that's carbonate. So what would be carbonite?
CO2.
That's right. CO2. And don't forget the charge, 2 minus. That's going to be called carbonite. Okay, so then what if I have CO2 minus? What would that be called?
Carbonite.
Carbonate.
That's right, hypocarbonite. And if I have CO4 2 minus,
Percarbonate. Percarbonate. Percarbonate.
percarbonate, that's right. Okay, so remember the per is going to go with the 8, the hypo is going to go with the ite. Okay, you guys see how that works?
Yeah.
Good. Okay, so the other thing is things that are in the same group on our periodic table are going to behave similarly, right? What do I mean by that? So if I have, let's say we have group 15 and we have AsO5, 3 minus. So if we go to our polyatomic ion table, and first off, let's see, As, what other members are in the group with As?
Nitrogen.
Nitrogen. Okay, now I'm going to tell you this now. Nitrogen is always going to be an exception because it's an oddball, and then I'll show you why in a minute. But the other one is what's right underneath nitrogen?
Phosphorus.
Phosphorus. So what we're going to do is we're going to go to our polyatomic ion table, And then we're going to look for that phosphate. Do you guys see phosphate anywhere?
Right at the bottom.
Right at the bottom.
PO4. Yeah, PO4, 3 minus.
Okay, so we see it right here. Okay. Okay, so we have our PO4, 3 minus. And we know that that is called phosphate. So if we had arsenate, I'll type that out. We would expect it to have the same chemical formula as the phosphate, same number of O's as the phosphate, except it says AS. So our chemical formula for arsenate is going to be AS O4, 3 minus. Okay, so that will be the chemical formula for arsenate. So things that are in the same group are going to behave similarly, right? So that means that when they form these polyatomic ions, they're going to form very similar to what you see. So this guy is called, as I said, arsenate. So then what would be AsO5 called? 3 minus.
Perarsenate.
Perarsenate. Oops. Okay. Do you guys understand and see that?
Yes.
Okay. Okay, so now how can we use these guys, right? We know that they're ions. We know that they're acting together. So if I have, let's say we're going to talk about that perarsenate. Let's say we have Mg, and we know that, what is the charge on Mg?
Positive, 2 positive?
That's right, 2 positive. So if I have the perarsenate and I have magnesium, the magnesium ion, what is going to be my chemical formula if they bond together? And then what is going to be the name?
Could you repeat that again, please?
Yeah, so if I have the magnesium ion and my perarsenate ion, what would be the chemical formula and the chemical name of that compound?
Wouldn't you just stick the O5 -3 charge with the Mg2 plus?
So you have to put the AS too, because that's all together is acting as
Oh,
perarsenate.
okay.
Yeah. So, but what are the charges? This is a 2 plus, and that's a 3 minus. Are those charges balanced?
No.
No.
No. So we need to make sure that the charges are going to be balanced. So how many magnesiums am I going to need? And how many perarsenates am I going to need?
Manganese 3.
3.
Okay. So I'm going to need 3 magnesium, not manganese. And
Magnesium.
yeah. Okay. And then how many perarsenates am I going to need?
Would it be 2?
It's going to be 2. That's right. because that adds up to -6, and that's +6. So my chemical formula is going to be Mg3. And then here, we're going to use parentheses because we're talking about having 2 of the perarsenate. And then outside of the parentheses, it'll tell us how many we have, which is going to be 2. Okay? And the name of the compound is going to be called it's not going to be called whiskey. What do you guys think?
Tequila. Eh?
Tequila. I wish. Okay, so let's give it a shot. What is that metal called?
Is it magnesium? I don't know. Arsenic? I don't know.
Or
So you need the per,
That's
you need
right.
the per, right? Perarsenate.
Perarsenate. That's right.
Oh yeah, I'm getting it.
Oh yeah, good.
Wait, so we put the parentheses because it's a polyatomic ion, so we want to distinguish that,
Yes, it's
right?
for 2 reasons. Because we need 2 of them, right? And we're talking about the polyatomic ion. So anytime that you see parentheses, you're talking about a polyatomic ion.
Okay.
Okay. In most cases, when you have a metal and then in front, you're talking about a polyatomic ion. There are some cases in OChem that you use parentheses, and that usually means that we have multiple copies of that as well too. And so those are like chains that are hanging off of other. But that's an OChem. So. Okay, questions? Okay, so what if I had, let's say, these two? We have Fe3 plus, and let's see, SCN minus. Okay, so what would be the chemical formula?
Well, first you need to balance the charges, right? So the SCN would have a 3.
Okay, so I need 3 of them. Okay, so I need SCN 3 copies of it, right? I can't just change that one charge, so we're going to need 3 copies of it. Okay, so then my chemical formula is going to be what?
Fe3 plus SCN 3, yeah.
Okay, so let me see. It's going to be parentheses. Is there going to be parentheses in there?
Yeah.
Yes.
SCN. And I'm going to close my parentheses. And I'm going to put a 3. I'll move this over so you guys can see it.
And we don't have to write the charge, do we?
Nope, we don't have to write the charge. We shouldn't write the
Yeah,
charge.
because we balance it out.
That's right. Can you guys see if it's over here? Okay, so then what would be the name?
Iron per something,
Iron.
right?
Okay, but what do we know about iron? What type of metal is that?
It's transition.
It's a transition metal. So what do we know about transition metals?
Oh, they need to have their Roman numeral thing, right?
Okay. So that's right. I need the Roman numeral 3. Let me know that it has a 3
Mm,
plus charge. Okay. And then what is SCN called?
Theos, I don't know,
Uh,
thiocyanate.
Thiocyanate. Okay. And that's it. Okay. How do you guys feel?
Okay.
Okay. You want to try one more?
Yes.
Okay. So let's do one a little challenging here. Okay. Okay. I know what we'll do. Okay. So let's do. Okay. Can I clear? I'm going to clear all of my writing everywhere so I have room to write more. Okay. So what if I have, let's do, what if I have these two ions? What would be the chemical formula and the chemical name?
Number. Would that be hypomagnite or no? Should I push one?
You're close. You're close. So we know that it has a single minus charge. So we wanted something that's going to have the Mn and it has a minus charge, not a 2 minus charge.
wait, so you want us to balance it, right?
First, let's figure out she's on the right track. Let's try to figure out
Oh,
what
for the
ion this is.
oh,
So if this guy is called permanganate, and it's in this case, it's called permanganate because it only has a single charge. It's a weird case. So then if it has 2 minuses, then what would we call that?
just magnate, right? Or
No. So this one again, it's a special case. So permanganate is MnO4 minus. Now, manganate is MnO4 2 minus. So this here is kind of like our starting point, right? So if I have MnO minus, I mean O3 minus, right? We would call that one per, which again is so weird, permanganate. Yeah, night. And if I have one that's less than permanganate, what is that going to be called? So MnO2 minus, which is what we have, that one's going to be called what? So what would be less than ite?
Hypo.
Right.
Hypomanganate?
Hypopermanganate. Yeah, this one, like I said, is a special.
Oh, hypoper. Give me it. I need to write something. Give me it. Child. Thank you.
Why are you laughing?
Because he can hear. Say hi.
Hi.
Hi, how are you? This is one of the best things about teaching online is, you know, I know some of you guys are so worried about having your kids and everything. I love it. It makes me laugh because they're watching what you're doing. They're watching you study, right? And that sets a great example for them. And then they're also such a nuisance to you guys. It makes me laugh. So I enjoy it quite a bit. So hypopermanganate. Okay, so that's going to be this ion, right? So how many of them are we going to need to balance out that 6 plus?
6.
We're going to need 6 of them, right? So then we're going to have Bi parentheses MnO2, and I'm going to put a 6 there. Okay, so then we would call this, what will be the chemical name? What is Bi?
Bismuth.
Bismuth. That's right. So we're going to start off with bismuth.
Then don't you need the 6 Roman
That's right.
numeral?
Roman numeral 6. And then we put hypo permanganate. Or yeah. That is a horrible looking word.
Wait, so it has hypo and per. So does that mean like it's like higher and lower than the regular one, like H?
Yeah.
Like
So
I don't get it.
yeah. Hey, no, what you very good point, right? So the problem is that permanganate, right? Permanganate means something different than manganate. It's the difference between permanganate and manganate in this case is just the charge. You have only one minus here, and you have two minuses for the manganate. So when they first named this compound, right, it went off as permanganate. They used that per in this situation, and it's stuck ever since. And so it was something that was called common name And because it has a common name, they didn't want to disrupt the system too much. So they kept this one as permanganate and this one as manganate. Where typically, when we talk about per, that means that you're adding oxygens. Here, you're not adding oxygens, right? Because don't they have the same
So,
number of oxygens?
okay, so it's just like its terminology.
Yeah, it's a weird one. And that's why I said,
Okay.
this one is a little weird one. Yeah. And I like to give you guys something like this because, we have these rules, but sometimes the rule makers break the rules. You know what I'm saying? So,
Yeah.
so are you guys feeling pretty confident about the about writing the formulas and everything like this? Like here we have ammonium bromide and we have ammonium sulfide. So what would be the chemical formulas for these guys? Okay, ammonium.
Oh, I'm sorry.
There you go.
For bromide, NH4Br.
Okay. And sulfide for the ammonium sulfide.
NH4 again. S.
So how many NH4s should we have?
2.
We
2.
should have 2. So I need to put my parentheses and 2. Okay. You guys are good? Good. Okay. What about the chemical formulas for aluminum oxide and barium nitride?
For aluminum oxide, do we
Cl2.
need
Oh,
2
sorry.
aluminum and 3 oxygen?
All right. For the aluminum oxide, we'll need 2 aluminum and 3 oxygens. Okay, Noah, you got the next one?
My bad. 2 barium. Well, no, 3 barium, 2 um nitrogen.
Okay. Okay, good. So I'm going to show you guys a little quickie here. So if I have aluminum and I know my aluminum is 3 plus and my oxygen is 2 minus. So what I can do is I can actually, because these are not multiples of each other, they're not divisible by each other. So then I can actually do it with like kind of like cross multiply. So your aluminum will end up with 2, and then your oxygen will end up with 3. Don't worry about the sign, okay? Because then that'll balance them out. Okay. Okay, so we already talked about the Greek prefixes and everything like that. So let's see. See if you guys can name these compounds.
The first one, the ally, that's for lithium, right?
That's right. Lithium what?
Is the
Bromide.
Br bromide?
That's right.
Okay.
Okay. What about the next one?
Magnesium iodide.
Okay, what about the next one?
Silver nitride.
Now, silver is going to be an exception because silver is always going to be a +1 charge, 99.9% of the time. There's that 0.1 that you may get something weird, but so most of the time it's going to be a +1 charge unless it says otherwise. Okay, what about this last one?
Manganese chloride.
Okay, what do we know about manganese?
Oh, it's a metal.
Drew, what type of metal?
Transition.
So then, so what do I need if it's a transition metal?
The Roman numeral thing.
Okay, I need the Roman numeral. So what would be the Roman numeral for this?
Uh,
2.
That's right, it'll be 2. The charge on manganese has to be a 2 because each of the chlorides are -1,
1.
2 of them. That's right.
oh, okay. All right.
You said. Okay. Okay. Acids. Okay, so when we talk about acids, the simplest definition of an acid is the addition of that H plus, or in this case, we call it the hydronium ion, which is this H3O plus. So all that is you have water, and then you have this H plus that's going to attach to it. So this H plus is also called a proton donor because if you look at this guy and you look at the number of electrons, neutrons, and protons, it only has a proton. So that's the reason why it's called a proton donor. So it's going to connect to the water and form a hydronium ion. And it's kind of clingy, right? So it likes to get attached to that water, thanks to that stuff. Now, when acids form, that H plus is going to be removed from, in this case, our hydrochloric acid, and it's going to go and attach to the water. Okay, just for simplicity cases, a lot of times what we'll do is we'll say HCl, and of course we're talking about it being in water, AQ. We'll just write it as H plus AQ, which is really the same thing as this hydronium plus Cl minus, so that we can keep track of how many pluses we have, H pluses we have. Now, when we talk about acids, we have a couple of strong acids or a couple of common acids, and I'll show you the common acids here in a second. Okay, so we have carbonic acid, which is H2CO3. We have nitric acid, which is HNO3. We have phosphoric acid, which is H3PO4. We have sulfuric acid, which is H2SO4. And we have chloric acid, which is HClO3. Okay. Now, one way that we always try to make a distinction between an acid, we often will make it aqueous because it helps us remember that acid is present. So often we'll see it written as H2CO3 AQ. Okay. So when we talk about those acids, we're going to be using that H plus, and that H plus has to balance out the charge that's going to be associated with the anion. And I'll show you what that means later. Now, the acids that we're talking about, most of them are going to be oxy acids, oxy for that oxygen, right? And acids because they have that H plus that can be removed to form that hydronium ion. Okay, so here, since I told you already, when we talk about groups, right, the elements that are in the same group are going to behave similarly, right? Elements in the same group will behave similarly when we're talking about our polyatomic ions and also when we're talking about our acids. So in this case, HClO3, I told you earlier, is called chloric acid. So HBrO3 is called bromic acid. So if I have HiO3, what do you think that's going to be called? Now, don't all you guys yell at once.
Iodic acid.
Idoic acid, that's right.
Idoic.
Okay. And so that's also going to be the same case for other chemical families or other groups. So in the case of sulfur, even though this is the British spelling for sulfur, selenium and telluride. So because they're in the same group, they're going to behave similar. And that's the same thing with phosphorus, again, British spelling, and arsenic. And we've already kind of talked about that with our polyatomic ions. So given that the name of H2SO4 is sulfurous acid, what is the name of H2TO4?
Telluric acid.
So remember, if they're in the same group, they're going to behave similarly regards to the number of oxygens. So in this case, this is called sulfurous acid. Sulfurous acid. So then this guy is not going to be telluric. It's going to be, since we have
Tellurious.
tellurious. That's right. Tellurious acid. Okay. Now, if you look on your polyatomic ion table, flip it again, maybe. Okay, do you guys see that? I'm going to see if I can make it big. I ate organic apples despite them being poisonous. So we have ate and ick are going to go together, and ite and ous. And then you have down here, my ride has hydraulics. Ride and then hydraulics. Okay, let me show you what this means, right? So if we have, let's say, for instance, we have H2SO4. So we know that this guy is called sulfuric acid. Okay, so if we take a look at this guy, this here is a polyatomic ion because we know that this is going to be H plus that's going to be coming from. So in this case, this guy is SO4 2 minus. And then, of course, we have 2 H pluses. Okay, now this here is our polyatomic ion. What do we call this polyatomic ion? What is the name of it?
That's a -2 charge, right? Sulfate.
That's right. So we call this guy sulfate.
Sulfate, yeah.
Okay. Now, sulfate ends with ATE. So what we're going to do is we're going to drop that ATE. And then in the case of sulfur alone, we're just going to go ahead and put that
Sulfuric.
Yep. And then we just put ICE at the end of it. And then we put not ICE, IC, and then acid. Okay. So we call this acid sulfuric acid. Okay, so if we have, let's say we have silicate, right? So we have H2SiO3. Okay, so what would we call this acid? So we know that silicate ends with ATE, right? This is that same root for silicate, ATE. So what am I going to drop? And then what am I going to replace it with? So what does silicate end with?
ATE, so you have to replace it with the ick.
Okay, so we need to replace it with the ick. So when we name the
Silicate.
acid, we
Is
call
that
it silic. Silicic. So I guess that's right. Silicic acid. Okay. Now, if we have, let's say we have hypochlorite, hypochlorite. So if we have HClO, what would we name this acid? So we're going to keep this first part, and it ends with ITE. So what does it say up here?
Os.
Os. Okay. So we're going to call this
Hydrochlorous acid.
That's right. Hypochlorous acid. Hypo.
Hypo.
So basically that sentence just helps us translate it into like an acid.
That is correct.
Okay.
Yep. It just helps us remember that ITE goes with changes to OUS and ATE changes to IC. Okay. And that's when we're talking about acids. Okay. So this last one, my ride has hydraulics. So when we have, in the case left, HCl, we know that this guy is called the chloride ion, right? Because we know it's Cl minus, and that's going to be H plus in this case. Now they're coming together to make this acid. So it's this case, this guy would be called hydrochloric acid. So when there's no oxygens, we're going to put that hydro there, and we're going to put ic and acid. So that's where this comes from. when you know that it's a ide, a hydride, or I'm sorry, chloride or fluoride or bromide or or sulfide, then in those cases, we're always going to put hydroic. So if I have H2S, and I want you guys to pay attention to whether it says AQ, because AQ, it forms an acid when it's in aqueous conditions. Okay? The hydrogen, we have the hydrogen in front, and you have AQ, that's going to be an acid forming situation. Okay? So this guy would be called hydrosulfuric acid. Okay? What would this guy be called?
Would it be hydrophosphoric acid?
That's right, hydrophosphoric acid. Okay? Okay, so given the formula perchloric acid is HClO4, what is the formula for perbromic acid?
HBr04.
Okay, so one of the reasons why I want you guys to get in a habit of seeing let's say you said HClAQ. So we know that that's going to be an acid. And then if we have HClG, in this case, this guy is going to be a gas. This means that it's covalently bonded. This here means that you're forming an acid. So this guy, as I said earlier, is going to be called hydrochloric acid. And that's going to be different than what we have here. This guy is going to be called hydrogen monochloride. Okay. So, and they're different from each other because this is covalently bonded. This here is ionically bonded. It's an ion. Okay. It's also sometimes called just hydrogen chloride gas. Okay. So this is just that table just kind of telling you how we'd go about naming things, that we just discussed. So name this acid. You guys should be expert at this one, right?
Perchloric acid?
Are you sure? Is there, you said perchloric? Is there a chlorine in there anywhere?
No.
Oh, no.
Okay. What is this root? Look on your
Uh,
college.
sulfate.
Is it sulfate?
Right? No, wait, let me see.
Sulfurous acid?
So yeah, so sulfurious. Yes,
mm,
that's right. It's sulfurious acid. Okay. So what would be the chemical formula for tellurious acid?
2 hydrogen, tellurium, and 3 oxygen.
You said how many?
Oh, 3 oxygen. Oh, two hydrogen, sorry.
2 hydrogens. Okay.
Tellurium
And
and 3 oxygen.
okay. We're going to put an AQ to make sure that we understand that it's an acid. Okay. So we've already talked about polyatomic ions. So that's our sulfate. So you guys are already familiar with that. We all often will call them oxo anions because they have oxygen in them and they're covalently charged. And so this is just showing you the relationship between the acid and the anion, what we already talked about. Okay. What is this anion called?
nitrate.
Nitrate or nitrite?
Oh no. Yeah, nitrate.
So it's a nitrite ion. Okay. So what would be the chemical formula for hypoiodite? Ion. So what does iodate look like?
IO?
Okay, so hypoiodite iodite is going to be IO and what charge?
Minus.
Minus. Okay. Okay. So this is just showing you how we derived our acids from our anions. And so that just shows you. Reinforces everything that you just learned. Okay, so now we get to test out your full range of naming. Okay, so MgBrO4 parentheses 2. What is that going to be called?
Is that one with the Greek prefixes?
Do we have a transitional metal there?
No.
No, so no Greek prefixes.
I meant Roman numerals.
Okay,
Sorry.
and we use Greek prefixes for covalently bonded things, but yeah. So and so Roman numerals, so no Roman numerals either because that's what we use for transitional metals.
Okay.
So what are we going to name it?
Alright, so that's the first one's magnesium.
Yeah.
Let me see the.
And the second one,
That's perbromate.
that's right.
There's an extra O.
That's right, because it has an extra O. That's right. So magnesium perbromate. Okay, so what would be the chemical formula for potassium cyanide? I'm sorry, selenite.
Two potassium.
So I have 2 potassium. What is the symbol for potassium?
Okay.
Okay.
My bad.
Okay.
Selenium. Let's see. And to top it all off, 3 oxygen.
Okay. Okay. So when we talk about acids, we're talking about that proton donor, right? So that's just that H plus. Um, so if we lose one of those H pluses, then we form, and it's kind of a weird thing, but we use a little bit of our Greek prefixes, which we use for when we talk about covalently bonded things. And we also use aspects of our ion. It uses a little bit of both. So in this case, this is called phosphoric acid. So if we lose one of the H pluses, it becomes dihydrogen phosphate ion. If we lose another one of those hydrogens, it just becomes hydrogen phosphate. And then, of course, if we lose all of our hydrogens, then we just have phosphate. Okay, so this process, the fact that you have multiple H pluses, it's protonated. Okay, so we're protonating things, or polyprotonated acid, meaning that it's able to lose more than one of those H pluses. So here's some examples of those. So here, if you have H2CO3, so that is going to be called our carbonic acid. If we lose one of those H's, then it becomes hydrogen carbonate. Okay, if we lose both of those H's, we have, this guy, that HCO3 is also called bicarbonate. So hydrogen carbonate or bicarbonate. This is its common name. In this case, we have sulfuric acid. If we lose one of those H's, it becomes hydrogen sulfide, or it's also called bisulfide. If we have sulfate, we lose one of them, we call this guy hydrogen sulfate. If we lose one in the case of the sulfurous acid, it's called hydrogen sulfite. And then we've already talked about in the case of phosphoric acid, if we lose one of them, it's called dihydrogen phosphate. And then here, if we lose another one of those hydrogens, it becomes hydrogen phosphate. And their common names, these here represent common names for them. So this one will be monobasic phosphate. This guy's going to be dibasic. Okay, so what would be the name of this compound?
Iron bicarbonate.
Okay,
Let me get
are we forgetting anything?
the
What do we have
chart,
to do?
the Roman numerals. I mean, you check the table.
Okay. So what is the charge on our bicarbonate?
Bicarbonate, it's just one negative.
Okay. And then we have three of them. So then what has to be the charge on that one iron?
A 3. So iron 3 bicarbonate.
Or we can also call it iron 3 hydrogen carbonate.
Why is it called bicarbonate if there's like no two?
So it's called bicarbonate because it's just a common name, and the fact that initially we started off with two hydrogens and we ended up losing one. And so they use that for that bi part. Started off with two, but you're down to one. Again, a common name, somebody said, oh, that's a great idea. That's what we're going to do. Okay, so let's write the chemical formula for ammonium hydrogen phosphate.
Hmm.
Ammonium hydrogen phosphate. Ammonium hydrogen phosphate. So what is the chemical formula for ammonium?
NH4 with a positive charge.
It's 7. 7.
And then I
Okay,
have one hydrogen,
one hydrogen.
and that is I think it's -1,
No,
positive.
because remember that hydrogen is going to go, yeah, it's going to come
Right.
with phosphate. Right.
It's been a long day because I wake up at 4 a.m. to get ready.
Oh, I know. I'm feeling you. I did. I didn't do 4 a.m. this morning. I slept in. I woke up at 6.
And then
Uh,
phosphate is PO4 with a 3 negative.
That's right. And it's 3 negative.
okay,
Well,
yeah.
phosphate is 3 negative normally, but now it's going to be different because we have that one H plus.
All right,
So
2 negative.
it should be a 2 negative actually. Okay,
Okay, 2 negative.
2 negative. Yeah.
So we
Because
just need a second ammonium,
so I'll need,
parentheses.
yes, that's right. So I'll need a second ammonia.
All right. Bracket 2 HPO4.
So okay, that's it. Looks good. Questions?
No,
Boy, we're trimming down. Everybody else is tapping out already.
maybe.
Yeah. Okay, so we have hydrates. So hydrates, all we're doing is adding water, right? So we'll have how we would name our ionic compound, and then we're adding water. So in this case, we have to tell us how many waters we have. So here we're going to be using those Greek prefixes to tell us the number of water. So when we use that term hydrate, that means water. Okay. So in this case, we have copper 2, sulfate, and then we have 5 water. So then we would call this guy
Pentahydrate.
copper
Oh,
2, sulfate. And then since there's 5 water, so we call it penta, like you said, hydrate. Okay. Now, when we remove that water, let's say in this case it's being removed, we would call this guy now copper 2, sulfate, anhydrous. Anhydrous lets us know that water has been removed. Now, this is important in chemistry because sometimes if we have water in things, that can cause things to blow up or cause some type of reaction that we don't want to happen. And sometimes our solutions come with water in it, and then we have to remove that water. Okay, so we're dehydrating it. So in that case, we use anhydrous. Anhydrous means getting rid of that water or without water. Okay, so how many water molecules are associated with each of the formula units of anhydrous sodium carbonate in, that is a weird thing, in Na2CO3 10H2O. So how many units of anhydrous, let's see, how many water molecules are associated with each formula unit of anhydrous ammonium carbonate? So this guy is anhydrous ammonium carbonate. How many waters are there attached to that?
there's 10.
There's 10. Okay, so then how will we name this hydrate?
Decahydrate.
Okay, so we call this, the full name of the compound would be sodium
Carbonate. Decahydrate.
Okay, so write the chemical formula for nickel 2 fluoride hexahydrate. Nickel 2. So what does that mean?
And nickel has a 2 charge.
Okay, so nickel has a 2 plus charge. So
So
then
that
how
means we
many?
need 2 chlorines.
Okay, so 2 chlorides.
And
Then we
6
do the
waters.
And then I need 6 waters. Okay, so let's put that all together. So we have nickel, Cl2, and then we put this big old dot.
of 6H2O.
There we go. Okay, metallic bonds. God, we're almost done. 4 more slides, 4 more slides. Can you guys handle it?
Maybe.
He said maybe. So when we talk about metallic bonds, all right, here, yeah, good. So when we talk about metallic bonds, we're talking about metals, metals interacting with other metals, or metal ions interacting with other metal ions. So when we know that ionic situations, we had our metals going to be positive, and then we have negative, our negative anion, and they interact that plus and minus, and that causes them to come together. Now, metallic bonds are going to be kind of similar to that. The only thing is that the metal is going to drop the electron next to itself. And so the electron is negatively charged. The metal now is going to become positively charged. It's going to delocalize its electron so that that electron will act like it's negative on its own, like the negative molecule or a negative atom. And then the metal itself is going to act like it's a positive atom because it's gotten rid of that electron. And it's going to interact and bond together because of that. And so you can use this concept with bonding two different metals. So, like, have you guys heard of rose gold?
Yes.
Yes.
Yeah. So, rose gold is just a combination of it's gold, it's a little bit of silver, and it's a little bit of copper. And it gives it that rose color. Okay. So here's the example. This is what I'm showing you, or explaining to you. So like here, if we had sodium, sodium metal. So sodium is going to drop its one electron, so it can form that stable sodium ion right next to itself. And then it's going to pretend like this guy is a total atom that's negatively charged, and it's going to interact with it. And because of that interaction, it makes that metal really strong. And so you get what they call a sea of electrons because each of those sodium atoms do exactly the same thing. And so they use it to interact by electrostatic forces, making it very, very strong. Now, in the case of ionic compounds, we can add water and disrupt that. But in the case of this guy, we can't because those electrons, even though they're being delocalized, they're so tightly bound to that original metal that water's not able to get in between it to make that separation. Okay. And that's going to be the same case that happens here when let's say we have magnesium. Okay. So we can make alloys by adding some other metals, melting it down and letting it mix up. And that's what we do a lot of the time. So if we talk about 18 karat gold, 18 karat gold is 75% gold, 12.5% silver, and 12.5% copper. Rose gold is less gold, more copper. It gives it that nice little rose color. Brass is going to be anywhere from 60% to 95% copper, 5% to 40% zinc. Bronze is going to be 90% copper, 10% tin. Carbon steel is like strong, really strong steel. What they do, they add a little bit of carbon to it, hence carbon steel. Pewter, 91% tin, 7.5% antimony, 1.5% copper. Stainless steel is 70% iron, 18 to 20% chromium, 8 to 12% nickel. And sometimes they'll have other trace metals in it, sometimes to give it a little bit of a different type of shine or a slight different color. Sterling silver is going to be 95.5% silver and 7.5% copper. Okay.
So is there a reason why they like mix those metals together? Like, is there some type of reason, or is it just for like aesthetic purposes?
Sometimes it's aesthetic, and sometimes it's to strengthen the metal or weaken the metal. So depending on what you want to do. So like for instance, bronze, the copper and the tin, it gives you a slightly different color, and also it strengthens that copper. And of course, the tin of gold too, right? The steel that makes it stronger. So carbonated steel is often used in building bridges and things to that extent. Stainless steel. The reason that we use stainless steel is because we don't want things to rust. So a lot of times that carbonated steel will start to rust over time. So if you look at the bridge, some of those bridges start to rust. So if they added a little more chromium and nickel to it, it allow it to be stainless. And then also if you add that carbon, it gives it that strength.
Oh, that's kind of cool.
So yeah, there's a whole area called material science. It's a great area to get into. Tons of devices and alloys and have been developed, to sit there for strengthening purposes, for aesthetic purposes. And that's the same thing with they've used a lot of hydrocarbons to sit there and make very strong pieces of material. Are you guys familiar with bulletproof vests?
Yeah.
Right? So
Yes.
that's an example of using that material science to sit there and make something that will block a bullet from coming in and penetrating you, hurting you physically.
It would depend on the caliber.
Of course. Yeah. But that doesn't mean that we can't develop using material sciences something that may be able to hold off on some of those other calibers as well too. We just haven't got there yet. That's the best thing about science, right? Because if
Yeah.
you think about it, where we started at, they used to use just straight metal to try to block off bullets and things to that extent. And they found out, well, if you got a better caliber bullet, you can penetrate that metal. Well, then you need something better than that metal to sit there and block it. So we've improved our technology. It's a lot lighter than the metal, a lot more effective as preventing the bullet from going through. So this is just a quick summary of nomenclature and some of the rules that are associated with nomenclature, right? And so if we have two nonmetals coming together, we know that we're going to be using those Greek prefixes, and we're going to be using "ide" at the very last thing that we have. We know about monoatomic cations. We know about monatomic anions. We know about polyatomic ions. And we know about ionic compounds, where we have to add them two together and they have to add up to 0. We've also talked about acids. We talked about polyatomic anions. Talked about the formation of acids using polyatomic anions. We've talked about hydrates. And so these are some of the rules that we went through for quick summaries. Any questions?
No.
I'm going to let you guys go rather than going over chapter 13 right now. So we're going to do a very brief chapter 13 next week, and then we're going to start chapter. It's a combination of chapters 7, 8, and 10. The
All
rest
right.
of 7, 8, 10. Because you guys have a little bit of 7, you had a little bit of 8, and you haven't had any 10 yet.